Hi, this video is going to cover Chapter 11 for our introductory chemistry class. This chapter is called Gases, and this chapter is kind of unique because it doesn't really depend on previous chapters, and there aren't any future chapters that depend on it. So it's kind of its own standalone topic, which is kind of nice. It is a math-heavy chapter, lots of algebra for us in this chapter. So it is a new subject, so just like in a lot of our other chapters, we are starting with some definitions and some conceptual stuff, and then we'll get into the math that backs it up. So we're starting with properties of gases, and we have talked about gases before. We're just, of course, getting into more details. But when we have a container of gas, the molecules are very far apart from one another. There's lots of empty space, and they're in constant motion. So because of these two things, all of these other properties can exist. So they fill up their container, and they take on the shape of their container. And both of these are because of their constant motion. They have a low density, especially compared to solids and liquids, and they're very compressible. And both of these are because of the lots of empty space. Whenever we have a mixture of gases, it's always homogeneous, and that's again because of their constant motion. And they're fluid, meaning they can flow through a container. If we pop a balloon, the gas flows through it. And so that fluidity is also because of that constant motion. The theory that connects a lot of this information and helps explain the gas properties is called the kinetic molecular theory, and these are the four parts of it. The kinetic molecular theory says that gases are a collection of particles in constant motion, so it makes sense, we've said that before. The second part says no attractions or repulsions between particles. So this means that when they run into each other, they're just going to bounce right off. They're not drawn towards each other as an attraction, and they're not going to push away from each other like a repulsion. They're just going to have some bounces off of each other, and it says like billiard ball collision. So on a pool table, that's the comparison here. And both of these two pieces of information are what allow the gases to fill up a container for volume and shape. So fill a volume and a shape. And the third one says a lot of space between the particles compared to the size of the particles themselves. And the last one says the speed of the particles increase with increasing temperature. So as the temperature increases, the speed of those atoms or molecules is also going to increase. Temperature, we know, is a form of heat, which is a form of energy, and so we're transferring that energy. If we are transferring heat energy into those atoms, it's going to get converted into kinetic energy, and they're going to move around a lot more. And then this empty space part here, this is what allows them to have a low density and to be compressible. So a lot of connections between kind of some real world properties of what we know about gases to what's happening on that molecular or atomic level. So this is really the same information that was on the previous page. Just a kind of a picture to go along with it. So if we focus on the one in the center here, our gas molecules are moving around. We can compress them, and they're just going to move closer together. We can expand it and give it more space. So going to the left is showing us that they're compressible. Going to the right is showing us that they fill up the given volume. So it's a good picture because it illustrates kind of both halves, the motion of the gas molecules as well as that empty space. So those two properties are going to help explain all of the characteristics we know about gases. One of the big properties about gases that's unique, so not something that liquids and solids deal with, is pressure. And pressure is a result of the fact that the molecules are constantly moving and having collisions. So pressure is the measure of force divided by area. We're not going to do the math that's associated with that, but it's important to know that force plays a role in it. And so there's three things that will change the pressure of a gas. The first one is the number of gas particles, and we abbreviate this with a lowercase n, and we'll see that show up in some of our math equations. But if we increase n, meaning we add in more gas molecules, then the pressure is also going to go up, because the number of collisions is going to go up. I often like to think of this as students in a classroom. If you put more, so everyone's walking around the classroom. If we put more students in the classroom, there's going to be more people running into each other. There will be more collisions just because there's more people in the room. The second one is the volume of the container. So if we increase the volume of the container, the pressure is going to go down because there's going to be less collisions. So again, if we think about this like all of us in a room and we're all walking around, if all of a sudden our room got twice as big, we would run into each other less because there's more space for us to spread out. Also, this is the opposite of social distancing, so obviously we're not doing this in real life. And then the last one says the average speed of the gas particles. So we know that this is related to temperature. So if the temperature increases, then the pressure increases. Because if the temperature is increasing, then the speed is increasing. And if the temperature goes up, and the speed goes up, that means the gas molecules are moving around a lot faster. So this is going to cause the number of collisions to increase, because think about if you're walking back and forth across a room, you run into the wall, you turn around, you run into the wall, you turn around. But if you're now running back and forth across the room, you're going to hit the walls more often. You're also going to hit the walls with more force. So the number of collisions increase, but the force of those collisions is also increasing. So changing that temperature is going to cause the pressure to go up for two reasons. Now, with these relationships, we're going to put them into mathematical equations. Before we do that, though, we're going to look at some units of pressure. So this is a table from your book. The most common ones that we use are atmospheres and millimeters of mercury. Notice that millimeters of mercury and torr are the exact same number. So everything in this column, these are all equal to each other, so we can use these as conversion factors. So we are going to do a quick little practice to do some conversions here. We're going to convert 863.2 torr into pascals and into atmospheres. So this is my given. This is my find. So I'm going to go back to that previous slide, and I can see right here, let me change colors. I have that many pascals per that many millimeters of mercury. There we go. So here's my given, 863.2 torr. Torr on the bottom, pascals on the top, and my conversion factor from the chart is that 760 torr is equal to 101,000 325 pascals. So we put it in our calculator, and our calculator says 115083.8. We're going to do our sig fig and unit check. Units cancel. We're left with pascals. We start with 4 significant figures. 1, 2, 3, 4. We look behind it. 1, 1, 5, 1. And then we're going to put zeros in there as placeholders for size. Because we're ending in zeros, we know that's not the best way to write it. So I'm going to convert that over to scientific notation. 1, 2, 3, 4, 5. There we go. We have the right unit. We have the correct number of significant figures. And we did our math right. All right, second conversion there. We're going to start with 863.2 torr. Now I already know that 760 torr is going to go on the bottom. But I'm going to go back and look at my chart here. 760 torr is the same as 1 atmosphere. So that makes the math a little bit easy. Click in the wrong direction. Here we go. 1 atmosphere. So I put it in my calculator, and my calculator says 1.135789. So same thing. Sig figs, units, torrs canceling. We're left with atmospheres. Same starting number, so still have those 4 significant figures. 1, 2, 3, 4. 1.13. That 5 is going to round up to a 6. Atmospheres. There we go. Okay, so we're going to talk about a handful of different laws. And in most of the laws, we're going to be comparing 2 or 3 variables. And the variables we're looking at, I'm just going to put them up here on the top so I can mention them real quick. Pressure, volume, temperature, and moles. N stands for moles. And we don't use M for that because M is generally the abbreviation for mass. So we can think of N as number of moles. That's where it's coming from. So in these equations, these laws, we're going to be comparing 2, maybe 3 of these variables, but that's also assuming that the other ones are constant. So let me show you what I mean. Boyle's law is the comparison of pressure and volume. So our equation down there says that P1 times V1 equals P2 times V2. So that means that the temperature and the amount of gas are remaining constant. We can change the other variables, the pressure and the volume, but the temperature and N, or the moles of gas, have to stay the same. And so that's just how these laws work, is we are only comparing 2, maybe 3 variables at a time. So what Boyle's law tells us is that the pressure and the volume are inversely proportional. And this is something we talked about a couple slides ago. But what this means is that if the pressure increases, the volume will decrease. Another way, if we think about just kind of in the reverse direction, if the volume goes up, there's a lot more space, and so the pressure will go down. And so this is our equation to relate those 2 factors together. Pressure and volume can be in any unit we want as long as we're consistent. What I mean by that is that pressure 1 has to have the same units as pressure 2. And volume 1 has to have the same units as volume 2. And so this is a way to compare 2 different scenarios. So if we have a balloon or a tire, those are the most common examples in this chapter because we have to think of things that are full of air. But if we have a balloon at a certain volume and a certain pressure, and now we're going to compress it, and so now it has a new volume, what is the new pressure? There's a lot of word problems in this chapter. So here's one more picture, and then we'll do a practice problem with it. But our picture is kind of illustrating what I just said. So in our first scenario here, we have a volume of 1 liter and a pressure of 1 atmosphere, and there's a little weight on the top. And so if we now have a bigger weight, so it's pushing down, the volume is half as big. We went from 1 liter to 0.5 liters. That's going to cause the pressure to double. So there's one got divided by 2 and the other one got multiplied by 2. So they're changing by the same factor, just in different directions. One's increasing while the other is decreasing. So let's practice this and kind of talk about how to read these problems, because I know that deciphering word problems can be really tricky. So this says a balloon is filled with 15 liters of helium. Now when I read these problems, I'm going to start listing the information I read. Volume 1, 15 liters at 2 atmospheres. And I know that's my pressure because that's a pressure unit. So pressure 1, 2 atmospheres, and 28 degrees Celsius. So temperature 1 is 28 degrees Celsius. What is the volume of the balloon? So I'm putting that volume 2 goes a question mark because it's asking what is the volume. So I know that's what I'm going to be solving for. What is the volume of the balloon if the pressure is increased to 5 atmospheres? Okay, there's a couple things I want to point out. The word increased. With these laws, something is changing and we now have a new set of conditions. There's an increase, a decrease, a cooling, a heating, a compressing, and expanding. Look for that action word that's telling you that something has happened to the object that we're reading about. You're also going to get 2 sets of numbers. So I have mine labeled as volume 1, pressure 1, temperature 1, and volume 2, pressure 2. So once that change occurred, we now have a new set of numbers. The third thing I want to point out is notice that we have a temperature 1, but we don't have a temperature 2. There's nothing in this story, in this problem, that tells us that the temperature has changed. And so what that really tells us is that we don't need that piece of information. And you know that there's always extra information in word problems which can make them tricky. So I'm crossing it off. We have a temperature, but because we don't have any more information about it, we can assume that it remained constant and it's not necessary for our math. So eventually we're going to have a handful of equations, but right now we only have Boyle's law. And that's good because our information we're given is about pressure and volume. And Boyle's law says that P1 V1 equals P2 V2. And we need to find V2. So I'm going to rearrange my math equation so that it says V2 equals. So I'm going to divide both sides by P2. So it's canceling out over there, and what I'm left with is P1 V1 over P2 is equal to V2. So now I can just plug in my numbers on that left-hand side of the equation and solve for my missing volume. So pressure 1, 2 atmospheres. Volume 1, 15 liters. Pressure 2 is 5 atmospheres. Now, we should be able to make a prediction about our volume. We know that the pressure was increased, and so because the pressure went up, our volume should go down. So our original volume was 15 liters. We know it should be decreasing. We might not have a good guess as to what it should be, but we know it needs to be less than 15. And so that's a good way just to kind of make sure that you're doing your math right. And then we also want to check our units as we're doing this. So here's why it doesn't matter what the units are as long as they're the same. Both of those atmospheres are canceling each other out, and we're left with liters. So I put this in my calculator. I have 2 times 15 divided by 5, and I get 6 liters. So the balloon went from 15 liters to 6 liters. So the change makes sense, the units make sense, and it all fit with our Boyle's law equation. The second law we're going to talk about is Charles' law. And Charles' law is the connection between volume and temperature. And Charles' law says that if the temperature increases, the volume increases. The pictures that are down there are a balloon on top of boiling water or ice water. I remember when I was in high school, one of the big things was that you would buy your friends a bouquet of balloons for their birthday. It was fun, but it was also kind of embarrassing for them because then they had to carry balloons around with them all day. And where I grew up, it was definitely cold in the winter, and inside the buildings, they kept it nice and toasty warm. So if you took your balloons outside, they would get kind of shriveled and wrinkled because it was so cold. And so remember, temperature is connected to the speed of the molecules. So because the molecules are moving much more slowly, they're not filling up that space as well. And then you take those balloons inside and it's so much warmer that now the molecules are moving around a lot faster and they fill up that space. So learning about the laws behind this, I always thought was an interesting connection. Our volume can be in any unit as long as we're consistent again, but temperature has to be in Kelvin. The reason why is because Kelvin does not have negative numbers, and so we don't want to have negative temperatures in there and have it mess up our answer, because we can't end up with a negative volume as an answer. So remember our Kelvin Celsius conversion here. All right, we're going to practice this one also. We're going to do quite a few practice ones in this chapter. Really, like every other slide is a practice slide. A balloon is filled with 2.5 liters of helium at 2 atmospheres and 25 Celsius. Oh, there's a little typo in there. What temperature must the balloon be if the volume is increased to 4.5 liters? So, a couple things. There's not any mention of a second pressure, so that was definitely extra information. My temperature is in Celsius, so I need to convert that. I'm going to add 273.15 to that. One thing I didn't mention on the last example is both of them mentioned helium. These laws actually aren't connected to what the gas is because there's so much more empty space than the gas molecules take up themselves. The gas itself is actually irrelevant because it's so small in comparison that it doesn't actually matter. Okay, so again, we have a comparison of volume and temperature. So I know I'm going to use Charles's law, V1 over T1 equals V2 over T2. And I'm going to solve for T2. So that means I need to do a little rearranging. And I'm going to do a cross multiplying. So I'm going to have V1 T2 is equal to V2 T1. So I multiplied, get a different color here. I multiplied across these two and these two just to kind of get rid of the fractions. And then I'm going to divide both sides by V1. So T2 is equal to V2 T1 over V1. And now I can plug in my numbers. So 4.5 liters, 298.15 Kelvin divided by V1, which is 2.5 liters. Now, same thing we did on the last one. Our volume increased. And so if our volume is increasing, that means our temperature should also be increasing. So I'm going to do 4.5 times 298.15 divided by 2.5, and I get 536.67. And we look at our units here. Liters are canceling, so we're left with Kelvin. So that could be our final answer, but because the original temperature was reported in Celsius, I'm going to convert this back to Celsius. So minus 273.15, and we get 263.52 Celsius. Let's check our significant figures. And significant figures, all of our starting numbers all had 2, so we're going to stop it right there, which means we will have 260 degrees Celsius. So the temperature definitely went up. We went from 25 to 260, so quite an increase. The next law is a combination of Boyle's law and Charles' law, which it has a good name. It's called the combined gas law. So we have P1 times V1 on the top, so representing Boyle's law, and we could think of it as V1 on the top and T1 on the bottom to represent Charles' law, but really we're just kind of putting them all together to get this equation. And so our practice problem here is, again, just going to combine all of that information. So a container is filled with 3.7 liters of air at 1.1 atmospheres and 28 Celsius. The container is submerged underwater. So the fact that it was submerged underwater tells us that some changes are going to occur to a pressure of 4.7 atmospheres and a temperature of 15 Celsius. What is the new volume? Okay, so our combined gas law, P1V1 over T1 equals P2V2 over T2. And I know that I'm solving for volume 2, so I'm going to do a little bit of rearranging. I'm going to multiply both sides by T2. So it's canceling out over there. And then I'm going to divide both sides by P2. So here's our final equation. Volume 2 is equal to T2, P1V1 over P2T1. So a lot of algebraic rearranging. We could have also just started with a cross multiplying and then did some rearranging if that makes more sense to you. So now it's just plugging in all of our numbers. But there is one more thing we need to do. I'm realizing as I say this. Our temperatures are in Celsius, and we need to convert them over to kelvins. So I'm going to add 273.15. There we go. So now we have some better temperatures to use. So temperature 2, pressure 1, volume 1, pressure 2, and temperature 1. Now we might be able to make a prediction here as to if our new volume should be bigger or smaller. It kind of just depends on if the change in the pressure and the change in the volume are supporting the same move, the same change. So our pressure is increasing, and an increase in pressure tells us that our volume should be going down. And our temperature is decreasing, which also tells us our volume should be going down. So our new volume should be less than 3.7 liters. So I'm going to put all of these numbers into my calculator. And my volume 2 is 0.82857. We got to do a couple checks here. Let's look at units, Kelvin, atmospheres. We're left with liters. That's great. We go back and look. All of our starting numbers were 2 significant figures, so I'm going to underline right there. Volume 2, 0.83 liters. So it definitely went down. We have the right units and the right sig figs. All right, the last law of this type, not of this chapter, but of this type, is called Avogadro's law. And so remember, Avogadro's number had to do with a mole and how many particles were in a mole. So Avogadro's law has to do with volume and number of moles for a gas. And our relationship here is that if the number of moles goes up, then the volume will also go up. So if you put more gas into a container, the volume will increase if the pressure and the temperature are constant. And so we have our equation there, V1 over N1 equals V2 over N2. So here's our practice for this one. A cylinder contains 2.00 grams of helium and has a volume of 2.0 liters. Helium was added, so there's our change, and now the volume is 2.7 liters. How much helium was added? So we have a starting mass, and we want to know the mass of added helium. That's what we're trying to find. This is going to use Avogadro's equation, but we need to do a little bit of converting first. And I have a mass, but what I really want to know is how many moles is that. And so I'm going to take my mass and I'm going to use my periodic table here to get to the molar mass of helium and get to the moles of helium. So 1 mole of helium is 4.0026 grams. So I put that in my calculator. So we have about a half a mole, but let's get a little bit more precise. We're going to have 0.4997 moles of helium. That is my N1. So my equation, Avogadro's law, V1 over N1 equals V2 over N2. So we have both volumes, we have the first moles, we need to find the second moles. So I'm going to do a little cross multiplying here to rearrange my equation. So I'm going to say that V1 times N2 is equal to V2 times N1, and then we are going to divide by V1. So remember, N2 is what we're trying to solve for. So we end up with N2 is equal to V2 N1 over V1. We're going to plug some numbers in here. 2.70 liters times 0.49967 moles divided by volume 1, which is 2 liters. Now we already know that this number is going to go up for a couple reasons. The volume went up, and it tells us that helium was added. So there's not really a surprise here. So we're going to plug it into the calculator. 2.7 times 0.49967 divided by 2, and we get 2.6982. Liters are canceling. We're left with moles. Now I'm going to underline my significant figures, but I'm not going to round quite yet because this isn't our answer. So that would cut off right there. The question says how much helium was added. This is the new amount of helium, and this is the original amount of helium. So if we want to know how much was added, we need to subtract. So the amount that had to have been added was 2.19857 moles. And we're going to cut that off at that 2 significant figure mark. So 2.2 moles were added. Now we could convert that over to grams if it was asking for it, if we needed to, but we can leave it in moles because it's not specified. And I ran out of space. All right, last law in this chapter is the ideal gas law. Now, we've done 4 laws: Charles, Boyle, Avogadro, and combined gas law. What those 4 laws have in common is that something was changing. The temperature increased, the pressure was decreasing, the volume was expanding, gas was added, there was a change that was occurring. The ideal gas law is what we use when we just have one condition. Here's our equation. This one right here in the middle is the one we want to focus on. PV equals nRT. P is for pressure, V is for volume, N is for the number of gas moles, T is temperature, and then R is this number. This is called the gas constant. It's what allows all of these 4 variables to be compared together. And in a question where you would use this, you know the pressure, and you know the volume, and you know the temperature, but how many moles of gas do you have? There's no change that's occurring. You're just missing a data point. Now notice the gas constant. The number is 0.0821, but notice the units: liters times atmospheres over moles times Kelvin. It has super weird units that don't really mean a whole lot, but they're there to make all of the rest of the units cancel out. So that means that when we do this problem, we need to have our pressure in atmospheres, our volume in liters. I'm going to cross that out because that is a typo on my slide there. And our temperature in Kelvin. So let me show you a problem where this will be used. If 1.9 moles of gas at 1,255 torr has a volume of 4.8 times 10 to the third milliliters, what is the temperature in Celsius? All right, here's what we know. 1.9 moles, 1,255 torr for the pressure, 4.8 times 10 to the third milliliters, and what is the temperature in Celsius? So if we think about our ideal gas law, PV equals nRT, we know pressure, we know volume, we know N, we know R because it's a constant. We're missing that temperature. So we have all of the variables except for one. We do need to do a little bit of converting. I need to change my pressure into atmospheres. So 1 atmosphere is 760 torr. So I get 1.651315 atmosphere. And we want to go from milliliters to liters. 1 milliliter is 10 to the negative third liters. And and that's it. So if PV equals nRT, and I want to solve for the temperature, I'm going to just do a little bit of rearranging here. So I'm going to divide both sides by N times R. So those cancel out. Temperature is equal to pressure times volume over N times R. So my temperature is going to be equal to my pressure, 1.651315 atmospheres, times my volume, 4.8 liters, divided by N, which was 1.9 moles, and times R, so 0.0821 liters times atmospheres over moles times Kelvin. So that's just our given value. That's let me point it out on the last slide again. It's right here. So that's just we'll use that same number in all the equations. One word of caution about that number: if you look it up online, you forget it, so you just Google it real quick. Pay attention to the units. There are different values of R that will change the units. So instead of atmospheres, it might have torr, or instead of liters, it might be milliliters. So there are other R values out there. Okay, so I'm going to put all those big long numbers into my calculator. 1.651315 times 4.8 divided by 1.9 times 0.0821. Let's look at units. Atmospheres, liters, moles, and we're left with 1 over Kelvin. So we have 1 over a fraction, which is the same as multiplying by the reciprocal. So we get Kelvin. Now, if we look back at units, we had 2, I think I said units. If we look back at significant figures, 2 of our numbers had 2 significant figures and 1 had 4. So 2 is the cutoff point. So that becomes 51 Kelvin. But the question was actually asking for it in Celsius. So I need to take my Kelvin and subtract 273.15. And I get negative 222 Celsius. Now we can't make the predictions for this one like we did on the others. With the other ones, our something was changing, and so we could predict how the other variable would react. But there's no changes happening here, so we don't really have a lot of predictions. One of the ways that gas experiments are used and the data is used is to calculate a molar mass. And so just as a reminder, molar mass is grams over moles. So one more practice problem. It says, what is the molar mass of a gas if 1.007 grams, so let me start my little list here, has a pressure of 0.87 atmospheres and a volume of 0.452 liters with a temperature of 23 Celsius. So if we're trying to find molar mass is equal to mass over moles. We want to have grams per mole. Well, we already have the grams. That was given to us. We can use PV and T and the ideal gas law to get us to the moles. So I need to change my temperature, 23 Celsius. I'm going to add 273.15 Kelvin to that. The other ones are in good units. So I'm going to solve for my moles this time. So the number of moles is equal to pressure times volume over R times T. So pressure is 0.87 atmospheres, volume 0.452 liters, R is our constant, 0.08, whoops, said it right, wrote it wrong, 0.0821 liters atmospheres over mole Kelvin, and times the temperature. All right, all of that goes in the calculator. 0.87 times 0.452 divided by 0.0821 to 96.15. And I know it's moles. I'm going to show my units canceling out here. Atmospheres, liters, kelvins. We're left with moles. And I get 0.01617, but we're not done. We need to put it into our molar mass equation here. So 0.007 grams divided by 0.1617 moles. And I get 62.2625. So we're going to check sig figs in units. Looking back at what I started with, it looks like 2 is the smallest value. So we're going to stop it at that 2. It's going to stay at 2. And my units, I divided grams and moles. Those don't cancel out, so we keep both of them. Grams per mole. Okay, so if you're calculating the molar mass of a gas, this is generally what you're going to do. Of course, depends on what's given to you, but if you're calculating the molar mass, usually you're given a mass, and then you're going to be given enough information to solve for the moles, and then you're just putting all that information together. So the last law we talked about was the ideal gas law, and we have 2 sets of conditions here, and on the left side it's labeled as ideal gas conditions. So this is when we are at high temperatures and low pressures. High temperatures allows our gas molecules to go really fast, and low pressures means that they're going to be far apart. This allows for all of those assumptions in the kinetic molecular theory to be true. There's lots of empty space. They're in motion, which means they're not going to be attracted to each other or repel each other. There's really no interaction between them. If, though, we have low temperatures, so now they move slow, and high pressures, so now they're closer together, we don't have ideal conditions anymore, because now they're moving slower and they're closer together, so that means that's going to allow them to interact. The little blue lines here is showing those interactions, and they could be attractions or they could be repulsions, but either way it's going to change their properties. So our equations that we've looked at only work when we are under ideal conditions. Now, for our class, that's the only type of condition we're going to be using for math. You just need to know that non-ideal conditions include low temperatures and high pressures. When we have a mixture of gases, the gases are behaving independently, and so we can think of them as a single gas in terms of their size and their pressure, but each gas individually has its own pressure, and this is called a partial pressure. And this pressure is going to be a portion of the total pressure based on the composition of the gas. So we have some numbers down here of percent composition in air of nitrogen, oxygen, argon, and carbon dioxide. And so the air we breathe is 78% nitrogen, 20% oxygen, and so on. We're going to use these percentages on the next slide, though. It's going to help explain something. So the partial pressure is the pressure from an individual type of gas. And if we take the pressure from gas A and the pressure from gas B and pressure from gas C and add them all together, we will get the total pressure. So each of these is representing a partial pressure. It's called Dalton's law of partial pressure. And then underneath that, it says that the partial pressure of gas A is equal to the total pressure times X. X is the mole fraction. So this is that percent composition we saw on the last slide, but in decimal form. So to get to this number, we would do our percentage divided by 100. So really we're saying that if 78% of the gases are nitrogen, then 78% of the pressure is nitrogen's pressure. So if the total pressure of the air is 1 atmosphere, then nitrogen's partial pressure is 0.78, oxygen's partial pressure is 0.21, and argon's is 0.01. So we're going to do this with some other numbers. So a container has oxygen and nitrogen, and the total pressure is 2.43 atmospheres. The pressure of oxygen is 1.02 atmospheres. What is the pressure of nitrogen? So you might see this in your head already. It is a fairly easy equation. The total pressure is equal to the pressure of oxygen plus the pressure of nitrogen. So we know the total pressure. We know the pressure of the oxygen, so we're just solving for the pressure of nitrogen. It really is just a simple subtraction here. Really the only way this type of equation could get complicated is if you were given different units and you had to convert units. And so that's not even going to make it complicated. That's just going to make it take longer. Oh, let's put some units. Speaking of units, let's put some units in. So the pressure from the nitrogen is 1.41 atmospheres. The second problem on here says a container has a total pressure of 1,220 millimeters of mercury. It contains 82% nitrogen, 12% argon, 6% methane. CH4 is methane. What is the partial pressure of each gas? Okay, so we have nitrogen, argon, CH4. I have their percentages right there. I'm going to rewrite those in their decimal forms. 0.82, 0.12, 0.060. To get to their partial pressures, I'm just going to take those numbers and multiply it by the total pressure. So if nitrogen is 82% of the gas, then it will also be 82% of the pressure. So I get 1000.4, and for argon 146.4, and 73.2. I'm going to erase my total pressure over here. So I'm going to rewrite these with sig figs and units. So looking back, the percentages each have two significant figures. So the pressure from the nitrogen is 1.0 times 10 to the third millimeters of mercury. We're using millimeters of mercury because that's what our total pressure was in. So we're keeping that unit consistent. Pressure of the argon is 1.5 times 10 to the second millimeters of mercury. And the pressure of the CH4 is 73 millimeters of mercury. Now, if we add these three together, we should get 1220. Because of rounding, because of sig figs, we might not get exactly 1220, but we should definitely get very close. All right, there we go. We have one more topic left. Reactions that involve gases. What we're doing here is we're combining the math we learned in Chapter 8 with our gas laws we've learned in this chapter. And the reason for this is the stuff we learned in Chapter 8 allowed us to go from grams of something to grams of something else. But with gases, we don't usually measure it in mass, we usually measure it in volume. And there's one more piece of information down here. It says that 1 mole of gas is equal to 22.4 liters at STP. STP is standard temperature and pressure, which is 1 atmosphere and 273 K. So as long as we're at STP, we can even use 1 mole is 22.4 liters. We can use that as a conversion factor as long as our conditions are standard. All right, so last slide, we're doing some stoichiometry. 2 more slides. I forgot about this one. This is kind of a crazy map, but believe it or not, it's actually going to get a little bit busier in our next chapter. We've added on gas. So using our gas information, we can convert to moles. And so we're using the ideal gas law as our way to convert here. And so if we know pressure, volume, and temperature, we can get to moles, or if we know moles and pressure and temperature, we can get to volume. Really, as long as we have enough information, we can solve for that missing piece. So let's put it into action. This is our last slide, last problem. In the following reaction, 3.12 grams of aluminum react to create hydrogen at a pressure of 1.5 atmospheres and 23 degrees Celsius. How many milliliters of hydrogen was produced? So I'm going to go back here just for a second. We know our grams of aluminum. We're going to convert that into moles of aluminum using its molar mass. We're going to convert that into moles of hydrogen using our ratio. And then we're going to convert that into a volume because we know the temperature and we know the pressure, and after we do the rest of the math, we will know the moles. I also like to list the information above or below the equation like that. Again, it's just kind of one of the ways that I organize the data that's given to me. So let's start with our given. 3.12 grams of aluminum. I have my periodic table here. I'm going to put grams of aluminum on the bottom, moles of aluminum on the top. My aluminum, 1 mole of aluminum weighs 26.982 grams. I'm going to convert that into moles of hydrogen. So moles of aluminum on the bottom, moles of hydrogen on the top. My equation's already balanced for us. So I have 2 moles of aluminum, 3 moles of hydrogen, and my math for this part is going to stop right here because the rest of it gets put into our ideal gas law. So 3.12 divided by 26.982 times 3 divided by 2, 0.173448. All right, couple things. I'm going to fill in my units, moles of hydrogen. I'm going to underline my significant figures, but I'm not going to round. I started with 3. I'm going to underline that third one. Now, PV equals nRT. We are given temperature. We're given pressure. We just solved for moles. We know we're looking for volume, so I'm going to do a little rearranging here. Volume is equal to moles times R times T over pressure. I just solved for my moles. Again, I'm going to underline that 3 so I know it's my last significant digit. R is our constant. Oh gosh. Let's try that again. And temperature, I do need to convert my temperature over to Kelvin. I'm going to put my units underneath there because I ran out of space. Divided by the pressure. Okay, lots of numbers to work with here. So the number of moles times 0.0821 times 296.15 divided by 1.5. The volume is equal to 2.81148. Couple things, units and significant figures, moles, Kelvin, atmospheres, we're left with liters. We look back at our starting information. We definitely had just 2 significant figures, so that becomes just 2.8 liters, but we're not done. This is asking how many milliliters, so we have one more conversion left to do. 1 milliliter is 10 to the negative third liters. So 2,800 milliliters. So that's a good test problem, a good practice problem, because we are using all of the information from Chapter 8 as well as that ideal gas law. And that is it for this very heavy math chapter. Thank you.